There we have Mario Kummer to tell us about MM curves.
Yeah, thanks for having me. Yeah, I will tell you what this stands for, so then maybe it will be a disappointment for Matthias. I'll tell it only later so that he's still excited following the talk.
Is this the first talk where M has not stood for a matroid?
Yes. And yeah, not matroid, not M convex set, not yeah.
Minimum.
Of course not.
Of course not. Yes. Yes. So yeah. So this will be as you pointed out, not a talk on matrix theory. It will be from real algebraic geometry, but there will also be some nice combinatorics showing up. And so maybe the first take-home message that I want to explain to you is like the following. So if you have a degeneration of a curve, I mean, can associate to this metric graph. And the take-home message maybe for the first part of the talk would be the degeneration of a real curve. Then you should get a look at the ribbon graph. You get this additional structure of the complex involution acting on your complex curve. And then this should be reflected in some additional structure of the graph. And usually people are not super familiar with the theory of real curves, so I give a brief intro. So we will work over a real closed field. So this is a field, an ordered field, which has a finite algebraically closed field extension. And the nice thing is that like every first order statement that is first order logic statement that is true with the usual real numbers, which is an example for a real closed field, is also true over every other real closed field. So there's, for example, examples for real closed fields are real Puiseux series, right? You know that the complex Puiseux series are algebraically closed. So it has a finite field extension which is algebraically closed, and you can put an order here, like by looking at the coefficient of the smallest power of epsilon, that we think of epsilon being infinitesimally small. And the field that I prefer to work with is the field of algebraic Puiseux series, which is the all Puiseux series that are algebraic over the function field in epsilon. So the nice thing is that these elements here can be identified with terms of semi-algebraic functions. So these really correspond to some functions, at least in a small neighborhood. So we can, any real closed field is a topological field by declaring the open intervals to be open and looking at the topology generated by these open intervals. Then this is usually becomes a totally disconnected space. But for semi-algebraic sets, there's still a good notion of connectivity. Namely, we declare a semi-algebraic set, which is a set defined by finitely many polynomial inequalities. Semi-algebraic set to be semi-algebraically connected if it cannot be written as a disjoint union of semi-algebraic open subsets. And then the theory becomes nice and every semi-algebraic set has finitely many semi-algebraic connected components and things like this. So real curves. So we have the complex numbers, we know, okay, first there's one discrete invariant, the genus, and then fixing the genus, there's a connected continuous space of curves. Over the real numbers, there are more discrete invariants. So let's let be a smooth X be a smooth curve. Genus G over our real closed field. And for me, a curve in this talk will always be complete, reduced, and connected, but maybe reducible. Yes. So then we can look at following discrete invariants. For example, we can look at the number of semi-algebraic connected components of the real points. And there's one more, which is usually denoted by A. A is one if you have the so C like closure. If so, you can look at the say complex points, and you take out the real part, and then we declare this to be one if this semi-algebraic set remains connected. And zero otherwise. For a smooth projective curve, connected, this can be like this can have at most two connected. So it's either one connected or it has. And yeah, so maybe.
These numbers don't change if I extend my real closed field to a larger real closed field.
I mean, if you're given a curve, and then you do base change to a larger, they don't change it.
Is this like the T or?
I don't know about, I mean, knowing the theory of semi-algebraic sets over arbitrary real closed fields, it becomes easy, but I don't think it's like just given from the definitions. I don't think it's, I think it's not, it doesn't just follow from the statement that I said, like from the Tarski principle. I don't think it just follows from that.
This kind of stuff we can learn by looking at any book on real algebraic geometry.
Yes. For me, I mean, this kind of stuff that I'm using, or that that is used for proving the answer to your question. That you can, yeah. For example, the book by Ochnak, Coste and Roy, Real Algebraic Geometry. Algorithmic Real Algebraic Geometry by Basu and Roy. These are good books that have these kinds of statements. Maybe just one example. So like this. So here you have So now, I mean, one could ask which triples can appear as which triples of natural numbers can appear as the triple. So this goes back to Felix Klein, of course, over the usual real numbers. Then it's the same over every real closed curve. So there are some constraints. So maybe, does anybody know upper bound on the R? G+1, exactly. So this is sometimes called Harnack's theorem, although it was proven by Harnack only for plane curves. Then, of course, like if you have no real points, then this thing will be connected. If what happens if you're in this maximal case, then this this complement of the real part cannot be connected, because one definition of the genus is the maximum number of circles that you can take out from the surface without disconnecting it. If the genus is G and you take out G+1 circles, then it must become disconnected. And there's a last one. If this space becomes disconnected, then this number must be. Then we can check. It's true for these in these two cases. Okay. And it was shown by Seppele and Zielhol that in some sense these are really the only discrete invariants. So if you fix these three numbers, then you can deform any two curves, smooth curves, by a family of smooth curves of this type.
Are you saying these are the only restrictions?
Okay. So yeah, sure. So these are the only restrictions. This is, of course, the yeah, so this is one statement which was due to Klein, but then there's another statement which is stronger, which says if you take two curves of this type, then you can deform them. So these are this is the discrete invariants. I call it the topological type of the curve. And one M I can now reveal is X is an M curve if there's the maximal number of real connected components. So this probably stands for maximal, but maybe audience. Yeah. Okay, so this is, I think, the stuff about real curves. There any questions on this?
I missed that point. You say they're semi-algebraic connected, but what was the difference to connected in the definition?
So in
XC minus.
but there's some.
Is this in complex? I mean, or in the algebraic closure?
Yes, you can, if you have the algebraic closure, this is a two-dimensional vector space over the real closed field, and then you put the semi-algebraic.
Thanks.
Yeah. So over the real numbers, over the usual real numbers, there's no difference between being semi-algebraically connected and usual connectedness, but others becomes very ill-behaved, the connectedness. Okay. So now we want to look at degenerations. And we take the following setup. We look at the valuation ring now we fix as a real closed field the algebraic Puiseux numbers, Puiseux series, and we look at the usual valuation ring in this field. This can be described, so this is an ordered field, can be described as the convex hull of the integers in this field. And we fix a schema over B, flat over B, such that the general fiber, right, so this valuation ring, so it has special fiber and the general fiber. So the general fiber X prime, this is over this real closed field is smooth of genus G, and the special fiber denoted by X naught. So this is curve over the usual real numbers. Want it to be a stable. Now, stable not in the sense of stable polynomials or something, but like deformation theory. So it's a connected projective curve which has only nodal singularities, and every rational connected components intersects. Every smooth rational component intersects every other component in at least 3 points.
And this is a condition over the algebraic closure.
Yes. Yeah, and regarding like this algebraic Puiseux series, if you take the point of view of terms of semi-algebraic functions, then this really gives like an actual semi-algebraic family of real like curves over the reals, which converges to the X naught, and where every family member which is close enough to X naught has the same topological type as X prime. Okay, and so now this X over B is Mumford if the dual graph of the special fiber. So the vertices of this graph are the irreducible components of X naught, and you have an edge if for every node the edge between the 2 points, at most two irreducible components that contain this. So the dual graph should have genus G. This is equivalent to all irreducible components of X0 being rational curves. And then some reality condition, all nodes curve are the intersection of real branches. So this means there are all singularities of X0 are real points, and they are not isolated. And say that X is an M curve if M is a maximal. The general fiber is M curve, and the special fiber is Sturmfels. Like the general fiber is in the real algebraic sense maximal, and this is in the combinatorial sense maximal.
Can you please define again the graph?
The graph? So the vertices of the graph are the irreducible components of X0, and you have an edge between two vertices if these irreducible components intersect in a node.
Thank you.
Yes,
And you don't get self-intersections.
then you get it.
Okay.
So it's okay to have a component which is irreducible but singular.
Yes, I mean, for the definition, the next step I will exclude this, but yes.
Really what is maximal?
Hmm?
Because you want it maximal.
You're saying then you don't get something which is maximal?
With one conductive component.
I mean, the general fiber should be maximal. So this, I mean, you can, I think this is something that can happen.
Said something before that two irreducible components intersect in at least three vertices. Did I understand this right?
The stable condition says that if you have a rational component, a smooth rational component, then this should intersect the rest of the curve in at least 3 points.
Yeah, but this can be different components. Right?
Yes.
Yeah. Okay.
Okay. I think now I should. Okay, now I want to, given this situation, like usually, like we have already associated a graph to this situation. One could also equip this with a metric like the length of edges. This we will not do in this talk, but we will give it this ribbon structure coming from the real structure. From now on, X would be as a path, X0 it should be Mumford, and I assume that this graph has no. Although this is would be an interesting setup, but results we don't have the results for this. So now the question is, given the X0, singular irreducible curve, when is it the limit of say M curves? Can we read this off from the graph? Are there combinatorial constraints on the graph when it can be the limit of M curves, or more generally, given the graph, can we decide which topological types can degenerate to this singular curve? And yeah, for this we associate to this situation a ribbon graph. Ribbon graph consists of 3 types of data: triple GCS, yeah, for now everything loopless, so G loopless graph. The extra information for every vertex V. C of V is a cyclic ordering of the edges at V. So this is C mapped from the set of vertices to cyclic, well, associates to every vertex, cyclic ordering of the edges that that are adjacent to V. This is not necessarily consistent. You can every vertex does its own thing. And every edge assign okay, so just so something like this. And if here at this vertex we also give a cyclic ordering, does not necessarily, these numbers do not necessarily.
Is the graph planar? Assume the planar.
I don't assume it to be.
How can you say cyclic? And what is it? And what does cyclic mean?
So a cyclic ordering on a set is like a ternary relation, which says that if you go from A, like, I mean, you just look at the set of edges, and then you on this set.
Somehow I was thinking it was forced on you by the.
No, it's not forced by the yeah, it's just
Okay.
could be like this.
That's
Just choose it in some way.
There was some like general theory, if you have some data like this, you can put your ribbon graph into an oriented surface or something like this.
Yes.
That recovers the given. What was that statement?
For this data is equivalent to the embedding of G to a not necessarily oriented compact surface. And in fact, a cellular embedding, which means that if you take out the graph, then you end up with finitely many open disks.
What is S in that picture?
Let me explain it in a few minutes. Yeah. Oh, okay. No, I mean I can do it now. Okay. So let's construct from a ribbon graph embedding to a surface. So ribbon graph compact compact surface. So the high level answer what the role of the S is that this makes it possible that you get non-orientable surfaces. There's also something that gives you an embedding of G to of this data to some orientable surface and to some orientable surface, but we want to be more general. So the idea of this construction is you have this graph, and then you take a certain set of cycles in this graph, and to these cycles you attach a disk. And I want to explain which cycles you have to choose to attach a disk. So if you have a cycle of edges, and we want that this edge is according to the cyclic ordering C at Vk, a neighbor of the preceding edge. So according to this cyclic ordering at Vk, the edge directly after or directly before this edge and now we also want to use the signs, then the cycle is good if for all k sorry. So we have two situations. Either this is the next one is the next edge in the cycle is according to the cyclic ordering at this vertex, the next or the previous one, and according to this we give a sign to the vertex. So we let Ek +1 or say 1 respectively, and then the cycle is good. If for all k, this Ek is the product of the signs that we have associated to the edges. So you go from one vertex to the next, and then whether the next edge that you walk is according to the cyclic ordering the next one or the previous one. This is determined by the choice you made in the previous step and the sign of the edge associated.
This be a simple cycle.
So, sorry?
This is going to be a simple cycle, like
I think it would work with non-simple cycles.
I'm just like if I have a tree and all the edges are one, all the sides are one, how does this work?
If you have a tree, then I think you will not.
I mean, if all the sides,
Yeah, I guess maybe leafless or something.
all sides are whole, then the tissue would always be positive. It would always decrease the, sorry, always increase the like number in the order. I don't think that's possible.
Yeah, maybe let's do some. Maybe let's even assume every vertex has at least 3, so that the cyclic ordering really gives you non-trivial information. Okay.
Why would 2 be left? Why would degree 2?
cannot decide.
Yeah, I mean, then it's not, it doesn't really give you, like, then the before and directly after would be the same, and then
Yes.
it's not be well defined. So. Okay, so maybe, yeah. Okay, so this gives you an embedding of G to surface. And we like, okay, but other construction is for X, like family of curves, real curves, you want to get a ribbon graph. Of which is the underlying graph is the graph we have already looked at. Then the cyclic ordering only depends on the special fiber, and the signs are determined by the by how the curve degenerates to your singular curve. So we choose, so to define the cyclic ordering, we choose an orientation on the real part of every irreducible component for every right. So we have the Mumford condition implies that these are all rational curves, the irreducible components, and the loopless condition implies that these are actually smooth rational curves. So the real part is always a circle, whatever this means over algebraically closed field. And then you can have a orientation either clockwise or counterclockwise, and then according to this you order the nodes which are correspond to the edges adjacent to this vertex. This gives you And the sign on the nodes like this, so you have your two so every node looks locally like this. You have the two rational curves intersecting, and then we have so here I have to be a little bit vague for the sake of simplicity. We have the real part of the family converging to this, and there can two situations can happen, either like this, it's coming from this side or from this side. Here we put a plus, and here we put a minus. Such situation. So maybe, okay, are there questions?
If I change the orientation of S1 to the opposite one,
Yes.
changing the cyclic ordering by like this to the other.
Yes. Yes, if you change the orientation on one component, this will reverse the cyclic ordering on this vertex and will reverse the signs on all adjacent edges.
That doesn't do anything to the surface sigma.
No, so there's one can define like an equivalence relation on ribbon graphs defined like this, and this is exactly the operation which makes it. It's reversing all these cyclic orderings and changing the signs. Okay, maybe I give the main results. If time permits, I can do an example. So let this be the topological type of X prime, and sigma be the surface that we get from first building this ribbon graph and then building the surface. So then the Euler characteristic of this surface is R plus 1 minus G. And A is 0 if and only if sigma is oriented. So from this we now get combinatorial restrictions on the topological types of curves that possibly can degenerate to X naught. Right? One thing is, if you want to have a curve of this topological type degenerating to X naught, then the graph, which depends only on X naught, must be embeddable to a surface satisfying these two conditions. So for example, if X is maximal Mumford curve, so it's a family of M curves converging to X naught, what do we get? We get R is equal to G plus 1. So this, the Euler characteristic must be 2, and there's only one compact surface with Euler characteristic 2, which is the sphere. So the graph must be embeddable to a sphere. And this must be a planar graph. So this, I mean, this is very much consistent with the theorem by Klein, right? Because if R is equal to G plus 1, then this is automatically a sphere, so it's automatically orientable. So we have A equals 0. So this is this thing. And if you want A to be 0, this must be orientable. Orientable surfaces have even Euler characteristics. So this part of Klein's theorem. So this matches up very well.
Can you say again, KSV is what?
The Euler characteristics. What?
KSV.
Ah, sorry. This is Bernd Sturmfels and Raluca Vlad. Sorry.
Just wondering, is there a natural degree R divisor on the graph? Because by reminiscence of Bacon-Riehn's Riemann-Roch theory for graphs.
A natural degree R divisor on the graph. Maybe, I mean, we can talk about, I mean, what? I don't know, maybe one can take one, like in the family, one point on every connected component and look at the limit, and then this might be what you want. I don't know.
So if your graph come from this way, so automatically every edge has degrees, every vertex has degree 3, or
And no, it can. I see. Yeah, let's. Every vertex has degree at least 3 by the stable condition. Yes.
as stable implies.
Yes.
It has degree exactly 3, right? It's stable in its G groups. Oh, you're not, yeah, but you're assuming it's Mumford. That,
Yes. Is it? Can't you have? I mean, can have genus? No.
I thought in MG bar, the maximally degenerate guys are all trivalent.
Yeah, but is Mumford the? I mean, at least this condition that I define, it's no way. It's not. And you can certainly have. I think, for example, n lines in the plane would satisfy the condition that I wrote down. But for the next theorem, I will assume that it's trivalent. But I think for this, it's not. It's not necessary. So we have a necessary criterion. So given singular curve, we have necessary criteria on the topological type for possible to degenerate to X0. We want to see whether this is also sufficient. So here we restrict to trivalent graphs. Oh, not yet, sorry. So we assume this is the singular curve is embedded in Pn. And H should be the Hilbert scheme, and we fix some orientations on X0, which gives us the, like on the components of X0, which gives us these cyclic orderings. And then there exist linear forms on the tangent space of the Hilbert scheme. Real linear forms for every edge. Such that the following holds for all B points of the Hilbert scheme whose special fiber is X naught. And so if you have such a point, this can also be seen as I already mentioned, as a semi-algebraic family, semi-algebraic curve or arc, semi-algebraic arc in the real part of the Hilbert scheme, which converges to X naught. And as such, we can define a tangent vector of this family at X naught, which might be zero if it's somehow ill-behaved, but you can define a tangent vector. So tangent vector okay, and now the statement is, so this if this is non-zero, in fact every set of these, each of these linear forms is non-zero in this tangent vector, then the general fiber is smooth. And the signs that we get from our family are exactly given by evaluating these lines, these linear forms at our tangent vector. So we have a hyperplane arrangement in the tangent space at our singular curve, and each connected component of the complement gives us a ribbon graph, so that whenever we approach this X naught from a direction to this connected component, this will be exactly the ribbon graph that we get from our geometric construction. So this is of course this theorem is very, I mean, everybody could prove it, because we do not assume that the LE are non-zero. I don't know if it's non-zero, in which situation it's non-zero, but if this is trivalent and X naught is canonically embedded, then the LE are really independent. And the point of the Hilbert scheme corresponding to X naught is the smooth point of the Hilbert scheme. So this being linearly independent means there's really, for every possible assignment of plus or minus to the edges, there is really one, there's exactly one component in the complement of the hyperplane arrangement. So we can always choose a vector in this set, and the point being a smooth point of the Hilbert scheme implies that we can actually find the family of curves that realizes this way. So this shows that that these combinatorial restrictions are in fact really the only restrictions that we can find in general for such determinations.
In this equation Sx of E equals Le of eta, you want to take the sine of Le of eta?
Yes. Yes, thanks. Yeah, I think there's some problems that I want to mention in this context. I maybe not write it down due to lack of time. So this is everything has been out looking at like the metric graph structure that we get from such a degeneration. This would be a thing that I don't know, given a metric graph and such a metric ribbon graph, can you realize it as the degeneration of such real curves? Then the other thing is, are there maybe also embeddings, singular embedded curves, where this thing gives a combinatorially interesting hyperplane arrangement? I mean, this is very nice for our purposes to prove that everything can happen, but combinatorially it's not a very interesting hyperplane arrangement. And the last very vague question is like, so you can look at the real points in the MG bar space and then look at which points correspond to M curves. And I think this should have some nice combinatorial properties or some nice topological properties. Maybe its closure is a ball, maybe it's a positive geometry. Yeah. I think this is maybe a hint because we only get planar graphs, the boundary. So some nice thing happening there. Yeah, I think that's what I would say. Yeah. Oh, okay. Yeah.
Do I understand right that the data that one gets there of the LEs is essentially an oriented matrix with underlying matrix uniform? Because we just care about the signs and the linearly independent.
Yeah, it's
uniform.
I mean, the matroid of this hyperplane arrangement is not just uniform, it's really like the uniform matroid of degree n in elements or something like this, right? Because all of them are.
Yeah.
But yeah,
So if you have a ribbon graph, then you get a delta matroid out of it. Can you read that off of, like, see that from the curve somehow?
You mean direct? I mean,
Yeah.
sure, but yeah, directly, yeah. Oh, I don't know. Maybe that's a direct way.
Any other questions?
I wanted to ask you about the comment you made about the combinatorics not being very interesting. I actually had the same question as Matt about. I mean, it seems like the regions of this arrangement are just kind of a walk around a bunch of different delta matrices. That sounds interesting to me. So, so I guess I wanted to ask you what you know about the combinatorics of these intersection matrix in the non-free matrix case.
Yeah, I mean, in other cases, yeah, I mean, actually, I haven't really tried to come up with, I mean, I very briefly tried, but it really tends to be very often linearly independent. I don't know an example where it's not linearly independent.
No further questions, let's thank the speaker.